Hello everyone, my name is MD Abdul Mirdad and I'm a postdoctoral fellow at the University of Alberta. Today I'll be presenting my research on development of span tables for mass timber panel concrete composite floors. First of all, we need to know about the mass timber panel concrete composite floor system. So a typical mass timber panel concrete composite floor system, as can be seen in the figure where a mass timber panel is connected to the reinforced concrete slab mechanical connectors. There can be a gap in between timber and concrete due to the presence of insulation layer. Under outer plane bending loading, the mass timber panel at the bottom resists tensile stresses, where the concrete slab at the top resists compressive stresses. An insulation layer can be provided in between timber and concrete for allowing better acoustic, vibration, and thermal performance. The shear connector, in this case, an inclined self-tapping screw, which penetrates all three layers of concrete, insulation, and timber, allows for partial shear transfer and therefore partial composite behavior. The structural efficiency of this composite system mostly depends on the performance of the interlayer shear connectors. The common fasteners used in composite floor systems is self-tapping screws as a mechanical connector and which are ductile. There is a substantial increase in strength and stiffness of the connection when they are inserted at 30 and 45-degree angle compared to 90-degree angle to the surface of the timber. This system is promoted by designer in the construction of modern multi-story mass timber building due to its higher strength and stiffness to weight ratio, larger span to total depth ratios, higher intensity, acoustic, thermal, and fire performance compared to the more conventional timber home system. Allowable floor span for the TCC system are often governed by serviceability performance requirements such as deflection and vibration, which are directly dependent on the effective bending stiffness. Therefore, the main objective of this study is to present an analytical model to better predict mass timber panel concrete composite floor system capacity, failure modes, effective bending stiffness, and load deflection responses. And finally, develop a allowable floor span for MTPC composite system based on the model. In the ultimate limit state, a floor system might fail due to the concrete crashing, timber crashing, or screw yielding when the stress demand exceeds the capacity at the concrete layer or timber layer, as well as shear connector respectively. The lowest capacity associated with these failure modes would govern the allowable floor span. In this system model, stiffness, strength, and ductility of the connector are considered in the composite system design. In the figure, you can see a mass timber panel concrete composite floor section, which are connected with inclined cross-pierce screws. Due to the external applied load, which is W, which is uniformly distributed loaded into the composite, the screw near the support, which is 1L, will yield first. Once the screw near the support yield first, the load will be distributed into the second and third screws. In this way, when the load has been increased into the composite, the second connectors will yield and load will be distributed in the third one. Similarly, they will yield simultaneously. So the load redistribution process is called the progressive yielding mechanism, which will lead to the elastic plastic analysis for the entire system. We need to check the stresses of timber, either in tension or shear, and concrete after yielding of each connectors. According to the superposition method, the simply supported panel is subdivided into two subsystems under uniformly load. In subsystem 1, the connection is released and the unconnected panel is analyzed under a uniformly applied load. In subsystem 2, the connectors are replaced by redundant shear force that act opposite to the slip caused by the first subsystem. The relative slip for the subsystem 1 can be calculated from this equation, and for the subsystem 2, the relative slip can be calculated from this equation. Therefore, after applying the compatibility condition, we can calculate the unknown interfacial connector shear force. So when we have more than one connector, this matrix can be solved and we can figure out the summation of all the connector force in X direct in the cross section. Once we apply the load and we need to apply the load into the system until the X are reached to until the X1 reached to its capacity. Similarly, we will apply load on the remaining connectors, like X2 and X3. Here the R is the number of connectors in the connectors row from the midspan. The midspan deflection for the two subsystems can simultaneously be calculated from these two equations. And after adding them based on the superposition method, we can calculate the total midspan deflection for the loads. The nonlinear load deflection response of MTPC composite system can be generated by calculating the load and corresponding deflection after yielding of each connector. As described in the previous slides, after once the first connector yields, the system will be no more linear. So based on this law, we can calculate our effective bending stiffness of the system. After yielding of the first connector, the load redistribute to the remaining connector. Then we'll get the second slope for yielding of the second connector. Similarly, third slope for the third connector yielding. So from the first slope, we can calculate the effective bending stiffness of the system, where del E, which is the midspan deflection, can be calculated from the previous slide. And after adding all the loads, after the yielding of all the connectors, we can calculate the ultimate capacity of the system. Similarly, the ultimate deflection of the system after adding all the connector, after adding the displacement after yielding all the connectors. In this figure, stress distribution in the MTPC composite has been shown. The axial stress caused by normal forces in subsystem 2 can be calculated from this equation, where XR is the summation of all connector force in cross direction, and this can be calculated from the metric solution that has been presented earlier. Then we can calculate the axial stress due to the bending in subsystem 1 from this equation, as well as for subsystem 2 from this equation. After adding up all the stresses, our main focus will be to get the stresses in this zone. So we need to figure out the stresses the top and bottom of the concrete, as well as bottom of the timber. Then we need to check the resistance of timber as well as concrete. So first of all, the extreme fiber stress of timber member must not be greater than its factor bending stresses. Similarly, critical shear stress in timber must not be greater than its factor shear strength. And we can check this from this presented equation, where FP is the specified bending strength of timber member and FP is the specified shear strength of timber member. For checking the resistance of concrete, we need to check the top extreme fiber stress of the concrete, which must not be greater than its factor compressive strength. Similarly, the bottom extreme fiber stress of concrete in tension must not be greater than its factor modulus of rupture. Where here in this equation, F prime C is the concrete compressive strength. This is how we can check the stress limit in concrete as well as timber. For the serviceability limit state, we need to check the deflection and vibration, which are really dependent on the effective bending stiffness of the system. That's why at the beginning, we calculate the effective bending stiffness of the system. So for the vertical midspan deflection, due to the specified load must not be greater than its allowable deflection. Here W is our uniformly distributed load, and effective bending stiffness can be calculated from the equation shown earlier in this presentation. And finally, the vibration control span limit for the composite panels can be checked from this equation, where we will need the mass per unit length of the composite. Once we check the serviceability in this state, we can check the other stuff like acoustics and fire. The sound transmission class is a main parameter to evaluate the acoustic performance of floor assemblies, which can be calculated from this equation. And for this equation, we need to find we need to know the mass of per unit area of the composite. And for the fire performance, the factor bending moment resistance of MTP by adjusting the section properties for fire performance can be calculated from this equation. Here you can see FB is our specified bending strength and SE effective, which is the effective section modulus considering the reduced cross section due to the charge layer. And this and this moment needs to be larger than specified bending strength, larger than the maximum induced factor moment in fire. The material properties used to develop the span tables are shown in the table. Here we use three thicknesses of concrete, 50, 75, and 100 millimeters. We use normal concrete of 35 MPa. We use GLT and CLT, use three thicknesses of GLT and four thicknesses of CLT. And finally, for the connector, we use self-tapping screws at 45-degree angle, and we only use one diameter of 11 millimeter. These connection properties were calculated based on a previous study of the author. With all these properties and parameters, the allowable span was developed for a particular MTPC floor system, satisfying all the requirements. The MATLAB software was used to perform repetitive calculation, which was based on all the design equations mentioned previously. Here you can see the span table, which has been developed based on the presented analytical model. So this allowable span is based on the failure modes of first screw yielding, concrete crushing, timber fracture, deflection limit, vibration requirement, and fire resistance requirement up to 1 hour. It was found that the allowable span were governed by the vibration requirement in all the cases. In this span table, you can see the concrete thickness of 50, 75, and 100 millimeter. We used two spacing, which is 250 and 500 millimeter. And we investigated two insulation thickness, 0 means no insulation and 5 millimeter insulation. As I mentioned, the GLT and CLT thickness earlier in this slide. Although an increase in concrete thickness can improve the acoustic performance of the composite floor, as can be seen in the table, it also tends to reduce the level floor span due to the reduction in natural frequency, which is detrimental to vibration performance. So when we have less concrete thickness of concrete, once we increase the thickness of concrete, we can see there is increase of the span length. But once the mass timber panel thickness increases, it actually increasing concrete, it actually decreases the span. It can be seen from both GLT and CLT. Then added insulation thickness was found to improve the acoustic performance of the composite floor significantly. Here the STC values have been shown where the deep green is the best performing in acoustic floor, which you can see for 5 millimeter insulation, like all the spans were performing better in acoustics. And then finally, all the structural performance improved with the decrease of the screw spacing. The serviceability performance was found nearly similar. So once we increase the spacing of the screw, we can see there is very less. Like we can compromise the span for up to 250 millimeter only. The major aim of this study was to demonstrate the application of the developed analytical model. Therefore, the span table was developed to meet strength, serviceability, fire, and acoustic performance requirements. This span table is limited to specific material properties only. Similar span table for different material properties can be developed based on different connection properties, concrete, and mass timber panel. I want to thank our sponsors for funding this program and want to thank you all for attending the presentation. Thank you.